Turns out that the polarity of bonds is not the most important thing. What's most important actually is the polarity of molecules. And so we're going to distinguish between molecules that are polar and nonpolar. And to determine whether molecules are polar or nonpolar, I can give you some definition, and if I would, here's what, don't write them down though, but here's what the definitions sound like. We talk about a nonpolar molecule. We describe a nonpolar molecule as one that has a symmetrical distribution of electrons within the molecule, and a polar molecule is one that has an asymmetrical distribution of electrons. But that doesn't really mean anything unless we look at some actual structures. So that's what we're going to do, is we're going to look at some actual structures, and based on looking at the structure of the molecule, we should then be able to determine its polarity. And so we're going to start by looking at HCl. And actually I'm going to write down several. What I'm going to do here is I'm going to write down the Lewis diagrams for each, even though you've done these before. We'll just go through and we'll write out the Lewis diagrams. This is for HCl. I remember that chlorine has an octet. Hydrogen has what we call a duet. And hydrogen's outer level is filled with just 2 because the first energy level holds a maximum of 2 electrons. All of the other outer levels have a maximum of 8, but the first level will hold just a maximum of 2. Then if we look at bromine, Br2, we would have drawn out a Lewis diagram looking something like this. And then if we drew out water, this is one molecule which I expect you to know the shape of. Horrible grammar, but that's what I expect. Not the grammar, the shape of the molecule, right? So what is the shape of a water molecule? Is it linear or is it bent?
Bent.
It's bent. Okay? And so this is the one that I expect you to know the shape, and you must know that water is a bent molecule. Then we have carbon tetrachloride. For carbon tetrachloride, we put the carbon in the center, then surrounded by the chlorine atoms. And then we put in the dots around each of these chlorines. And let's see, what else do we have? We have nitrogen trichloride. Now for the nitrogen trichloride, what I'm going to do here is I'm going to go to some molecules. I've built these 3-dimensional molecules and put them up here electronically. In fact, here's the HCl that we looked at before. Here's our Br2. Here's the water that we looked at. Here's the carbon tetrachloride. But now to get the correct shape down for the nitrogen trichloride, we kind of look at it here, we should see that this nitrogen kind of sits on top of the plane. It might be easier to see if we just look at the stick model, so we can see that that nitrogen sits kind of above there. And so we'll put down the nitrogen trichloride, showing its correct shape right here. So we'll show the nitrogen above the 3 chlorines, and then we'll put in the dots, and then we'll do the same thing here for the ammonia, which is NH3. If we look at the shape of an ammonia molecule, we see that ammonia as well has a shape kind of like a tripod, that nitrogen sits on the top. So again, we'll write out the nitrogen, and then we'll show it above the 3 hydrogens. Okay, so now what we want to do here is we want to determine the polarity of these molecules. Now, to determine the polarity, we go back to our table of electronegativities. We need to look up those electronegativity values. So in HCl, we look up the electronegativity of the hydrogen and the chlorine. And we see that we have value of hydrogen of 2.1. Chlorine we have 3.0. So we come back here. We have hydrogen sitting at 2.1, chlorine sitting at 3.0. Then the next thing we're going to do is we are going to determine the polarity of the bonds. Is this bond going to be polar or is it nonpolar? It's going to be polar. It's going to be polar because these values are
vastly different.
They are different from each other. And because they're different from each other, that means that this bond is going to be polar. So now, when we have a polar bond, we want to assign what we call partial charges. And these are not going to be complete charges because this is not an ionic bond. The electrons are not transferred from one to another. But rather, we go back and remember what the electronegativity stand for. Since chlorine has a large value, this means that the electrons spend more time with the chlorine than they do with the hydrogen. And if we think of the term electronegative or electronegativity, that means that this chlorine is going to be one that's more apt to have a negative charge. So we label it with a partial negative amount. And the hydrogen is going to have a partial positive charge. Now, if you make it into calculus, you're going to learn that these symbols represent a Greek letter delta, and they stand for partial amounts. And this means that this is partially positive, this is partially negative. It's not a complete positive, not a complete negative, but again, the one with the largest electronegativity value is always going to be assigned a partial negative. So if you remember what the word is called, electronegative, the one with the greatest electronegativity is going to be the one labeled partially negative. So now, once you have them labeled, here's how we determine the polarity of the molecule, which is the most important piece of this. What we do is we take a plane that is a flat surface, and we see if we can separate all the positive atoms on one side, all the partially negative atoms on the other side. We can separate the partial positives, the partial negatives, using a plane like we have here, then we have a polar molecule. And that's exactly what this is. This here represents a polar molecule. And it's polar because we have the partial positive hydrogen on one side, the partial negative chlorine on the other. Now if we go back to bromine, we have two like atoms bonded together. That means that the bond between them is a non-polar bond. The bond is non-polar. We can't assign partial positive or partial negative. So if all of the bonds in a molecule are non-polar, that means that the molecule is non-polar as well. We cannot put any partial positives and partial negatives in here again because these two atoms will share electrons equally. So it's an equal sharing. We don't even need to look up the electronegativity values because two like atoms bonded together will always share electrons equally. Well, then we go to H2O. We look up the electronegativity for hydrogen and for oxygen. We see hydrogen here at 2.1, oxygen sits here at 3.5. So again, hydrogen sits at 2.1, oxygen sits at 3.5. Now, of course, this time we have two bonds that are in there. So when we have two bonds and we want to look at the difference in electronegativity, we actually want to determine the polarity of each bond. And we compare them one at a time. So if we wanted to look at this bond, we basically cover up the other one. We don't divide up the electronegativities, we always compare these values. So if these values are different, then this bond is going to be a polar bond. The one that gets labeled partially negative is the Oxygen. The hydrogen gets labeled partially positive. We do the same thing here. We label them. Oxygen is going to get labeled partially negative. The hydrogen here partially positive. And again, that's simply because we compare these values. So we don't really show like there's two partial negatives, but we simply label it. It's a partial negative here on the oxygen, and each of these hydrogens is partially positive. Then we use the plane test. We want to use the plane test. And the plane test basically says if we can use a plane to separate, get all the partially positives on one side, the partial negatives on the other, then we have a polar molecule. So in this one here, we use the plane test. Here's our plane. And we get all the partial positives on one side, the partial negatives on the other. Yes or no?
Yeah.
Yes, we can. That means that this molecule here is a polar molecule. So again, water then is a polar molecule. Then we go to carbon tetrachloride. In the case of carbon tetrachloride now, we want to determine its polarity. And to determine the polarity of carbon tetrachloride, we look up the electronegativities of the chlorine and the carbon. So here we've got the carbon sitting at 2.5. We have the chlorine sitting at 3.0. So carbon sitting at 2.5. Chlorine sitting at 3.0. Well, then we start assigning partial positives and partial negatives. Partial negative goes to which element?
Carbon.
Partial negative goes to chlorine. Okay? Partial positive then would go to the carbon. Now, since we're drawing this in 2 dimensions, it might actually be easier to look at the 3-dimensional molecule for carbon tetrachloride. Let's zoom in on this right here. And now let's try to find a way to get all of the chlorine atoms on one side and the carbon atom on the other. Is there any way we can divide this up to get all the chlorines on one side and the carbon on the other? It doesn't work. And so even though the bonds in this molecule are polar, the molecule itself is going to be one that is a non-polar molecule. So again, this one here is going to be a non-polar molecule. I hate when this thing does that. Non-polar molecule. And so again, this is a case where the bonds are polar, but the molecule itself is nonpolar. In fact, we even really wouldn't need to look up the electronegativities of this one, because all we'd have to do is to look at the shapes of the molecules. And if we look at the shape of the molecule, we would see that no matter how we put this, no matter how we put it, and try to look at it, that carbon's always going to be in the center, and it's surrounded by chlorines the whole way. There's no way we can get this so the carbon's on one side and the chlorines are on the other. So that's regardless of whatever those electronegativity values would be, we look at the shape of the molecule. Then we go on to the nitrogen trichloride. In the nitrogen trichloride, this one here, we look up the electronegativity values. We see that nitrogen sits at 3.0, the chlorine sits at 3.0. So again, coming back here, nitrogen's at 3.0, chlorine's at 3.0, which means all of the bonds in this molecule are nonpolar. If all of the bonds are nonpolar, that means that the molecule is nonpolar as well. So this here is a nonpolar molecule. So any questions on any of them that we've done here? Yes, Dave.
So basically, whenever it's nonpolar, it's always going to be nonpolar.
Exactly. If, like in these cases here, you're talking about when the bonds are nonpolar.
Yeah.
Yeah, if all the bonds in the molecule are nonpolar, then the molecule is always nonpolar.
Okay.
However, if the bonds are polar, then what do we need to do?
Check to see if you can split them.
Right, then we need to check the shape of the molecule. That's where the three-dimensional shape comes into play. So here we can split them. We have the negatives on this side, the positives on this side. This one here we can split them. Positive on this side, negatives here. This one, though, we can't split. So even though the bonds themselves are polar, the molecule is still nonpolar because of that three-dimensional shape. Okay, anybody else? Yes, Gloria?
How do you put the delta plus and the delta negative again?
Okay. What do we call these values here? Remember what they're called? They're called the electronegativity. Okay? So, this is a mnemonic. This is a mnemonic, memory aid. So if you think of the word electronegativity, you have to remember that word, electronegativity. The one with the greatest electronegativity is the one that signed a partial negative charge.
Okay.
So just think electronegative, partial negative. Big electronegativity, partial negative is the one that's assigned. And so if one is the partial negative, then by default the other one is the partial positive. Okay, anybody else? All right, we've got a bunch of questions coming up in your Socrative app. Let's pull out your app here, and we have a question waiting for you. And this one now, just avoid the temptation of looking at that table in your text if you have it open. Based on what we learned, you can look at this periodic table. This is what it would be like on an exam. So if we do not have a table of electronegativities, and you look at the periodic table, which element would you expect to have the greatest electronegativity? 5, 4, 3, 2, 1. And it would be oxygen. Remember that electronegativity values increase as we go from
Left to right.
left to right. And as we go down within a group, the electronegativity values will decrease. So if we're looking at these 5 elements right here, that means that using carbon as a base, they decrease going down and they increase going to the right. So that would put oxygen in the position of having the largest electronegativity value. Next up, in molecules of NH3, and I'm going to show you that structure again here in just a moment. In molecules of NH3, and now you can use your electronegativity table if you need to, the bonds between nitrogen and hydrogen are they nonpolar, are they polar, or are they ionic? So if you need the electronegativity values, hydrogen sits here at 2.1, nitrogen at 3.0. 5, 4, 3, 2, 1. They are polar. And they are polar because
They're different.
the electronegativity values are different than each other. That's it. So hydrogen's at 2.1, nitrogen's at 3.0. So in NH3, the bonds are polar. So next up is NH3, comprised of nonpolar molecules, polar molecules, or ions. Now for this one, it would be helpful to know its three-dimensional structure. Here's the three-dimensional structure for ammonia. I'll show you here what it looks like with the sticks. So nitrogen kind of sits above the rest of them. 5, 4, 3, 2, 1. It's comprised of polar molecules. Now, this one's polar, because again, the three-dimensional shape is critical to this one. If we looked up those electronegativity values, we saw nitrogen again sat at 2.1. Chlorine, no, what is this? Hydrogen, what is it? I forgot them again. Nitrogen was at 3.0. Hydrogen is at 2.1. That means that the nitrogen here is partially negative. Each of these hydrogens are partially positive. And now if we can take a plane and separate all the partial positives on one side, all the partial negatives on the other side, then we have a molecule that is polar. So again, this is a polar molecule. If this is a flat molecule, then it's going to be nonpolar, but because that nitrogen sits above that partial negative, that makes this a polar molecule. Let's try another one. Next up, we have carbon dioxide. If you want to know the structure of a carbon dioxide molecule, here's what that looks like. Notice now that this is a linear molecule. We look at it like this. We can see it's still linear no matter how we look at it. So carbon is in the center of this. First question is, are these molecules, not the molecules, are the bonds polar or nonpolar? 5, 4, 3, 2, 1. The bonds are polar. And why are the bonds polar? They have a different electronegativity values. If we come back here, the electronegativity of the carbon sits at 2.5. The oxygen sits at 3.5. Now, I intentionally didn't tell you the values this time. We wouldn't need to know the values because what could we just simply do?
Look at the periodic table.
Look at the periodic table and remember that the values will increase as we go from left to right. So if we're going from left to right, we automatically know that oxygen has larger electronegativity value than does the carbon. If it has a larger electronegativity value, that means even without writing these numbers down, we could assign partial charges. Oxygen would be partially negative. The carbon would be one that is partially positive. Okay? So next question here on the Socrative app. Carbon dioxide. You need to know the three-dimensional structure. Here's what that three-dimensional structure looks like. Carbon dioxide comprised of polar molecules or nonpolar molecules. I think what's happening is you guys are getting the terms bonds and molecules mixed up. We consider the polarity of them independent of each other. This one here now is asking about the polarity of the molecule. 5, 4, 3, 2, 1. And these are nonpolar molecules. And now in this case, the molecules are nonpolar because if we try to separate positive and negative, one side on the other, what happens?
You can't do it.
You can't do it. No matter how we try to slice it here, the negatives are on opposite sides of each other. And so now another way you can think about this is you kind of think about it as like a tug of war. You can kind of think of these numbers over here as kind of be a strength at which these atoms can pull. So carbon's at 2.5, oxygen sits at 3.5. The difference in here is 1.0. And so what happens is that this oxygen atom is tugging electrons this way. This oxygen is tugging electrons this way because each one of them wants those shared electrons, but they are tugging against each other with an equal strength. If they're kind of pulling on each other in equal strength and their sides opposite of each other, their net effect is to cancel each other out. And when they cancel each other out, that's going to make them a non-polar molecule. So, any questions on any of these examples? Well, here's one you might ask. Who cares? I really don't care. Why should you care? Okay. Well, I'm not going to say that you'll care more after we look at this, but it is something that helps describe what it is that we observe. And it's the three-dimensional structure of the molecules that help us describe what these things do. And this is a general solubility rule. And that general solubility rule says likes dissolve likes. Likes dissolve likes. And what this general solubility rule means is this. It means that substances comprised of nonpolar molecules tend to dissolve in other substances comprised of nonpolar molecules. And substances comprised of polar molecules tend to dissolve in other substances made of polar molecules. Again, we're talking about the polarity of the molecules, not the polarity of the bonds. So again, substances made of nonpolar molecules tend to dissolve other substances made of nonpolar molecules. Substances comprised of polar molecules tend to dissolve other substances made of polar molecules. And then it turns out if a substance is really polar, it can also dissolve ionic compounds. So very polar substances can dissolve ionic compounds as well. So that said, what I have up here is a couple of burettes, and these burettes are filled with two different liquids. One of the burettes contains water, H2O, and the other one contains hexane. So one is water, one is hexane. And since we're going to have a test on this here next week anyhow, let's see if we can remember how we write out the formula for hexane. Hexane is going to have how many carbons?
6.
6. And what else is going to be in this compound?
Hydrogen.
Hydrogen. And so we simply surround it then with hydrogens all the way around here. So hexane is going to look something like this. Now we already talked about the polarity of water. How about the polarity of hexane? Is this going to be a polar molecule or is this going to be non-polar? We don't even need to look up electronegativities for this one. Because if it's polar, we should be able to separate atoms of one type on one side and atoms of another type on the other side. And can we separate carbons on one and hydrogens on the other? No. That must mean that hexane is a non-polar substance. So, when we look at water before, we said water is a polar substance. So here's what we're going to do. In these burettes, again, I have these two liquids, and I have them up here on the webcams. And what we're going to do here is we're going to see if we can, oh great, we can see that liquid really well. Come over here, let's make sure we can see this one. Yeah, we can see those. So we'll come back to this first one. What I'm going to do now is I'm going to take this balloon and I'm going to rub it in my hair to build up a static charge. And you're going to watch this on the screen. I'm going to put the balloon up to this liquid. We should see that nothing here happens to this one. So we'll come to this side here. We now see the liquid. I don't know if you can see that. Oh, sure you can. What's happening to the liquid when I bring the balloon up there?
It's diverting its path.
Diverting its path. So, first question here is this, and this is Socrative app. Which burette contains the water? The first one, which there was no attraction, or the second one, which there was an attraction? 5, 4, 3, 2, 1. And the second one was the water. And we would expect water, of course, to be attracted towards the comb because water is comprised of polar molecules. If it's a polar molecule, those have your partial positive and partial negative charges, and that then is going to be attracted towards a static charge that's built up here in the balloon. Now, I can also bring this over here and put it by the faucet. This is one of those things that you can actually demonstrate at home. This is what I call my kitchen chemistry demos. And if I move this aside here, what you're going to do, if you want to try this out at home, just try to get a thin stream of liquid coming out of a faucet, rub the balloon in your hair, and you should see, we'll do it this way, there we go, and you should see here how the water is attracted towards the balloon. And that's simply because of the static charge that we built up in the balloon and the fact that water is comprised of polar molecules. So, now, let's see, what else do we have? Oh, next question. I am putting some, and you don't need to answer this one yet, but what I'm doing here is I'm putting some water and hexane into these test tubes, and I'm trying to put approximately equal amounts into each one. So I put the water in here already. And somewhere I must have walked off with my other stopper. Here's one stopper. Here we go. All right. Okay, so now we have the water and the hexane. And remember that water, we say, is what type of molecule?
Polar.
Polar. And hexane is?
Non-polar.
Non-polar. So what's going to happen if I shake these up? Will they dissolve in each other? Or what should happen once I'm done shaking?
They'll separate.
They should separate if we have any luck here with this. It looks like, in fact, they are separating. And we're getting the two distinct layers back. So then the next question is, which layer is on top? I have the density information there. Which layer is on top? Take a look at your supplement app. Density of hexane is 0.66 grams per cubic centimeter. Water is 1.0 grams per cubic centimeter. That means which layer is on top? Oh, looks like we're all locked in. We'll check it out. All right, of course, hexane, because hexane is
Less dense.
less dense. That should be the one on top. So now, what I'm going to do here is I have some iodine, which is I2, and I have some cobalt 2 chloride here, which is an ionic compound. I'm going to place these into these two test tubes, and then I'm going to shake it up. And so, according to the general solubility rule, likes dissolve likes. Therefore, I2 should dissolve in which layer, and cobalt 2 chloride should dissolve in which layer. And I'm doing the iodine on your left. Get your answers locked in before I actually do this. Talk it over if you need to. 5, 4, 3, 2, 1. And then we'll look at it. This is how we're going to answer this one. Here's the iodine. This one is going into the one on your left. And then we will put the cobalt 2 chloride, the one that's on your right. And the reason why I picked these out is because they have kind of this nice pink and purple color. So again, iodine is on your left, cobalt 2 chloride is on your right. So now I'll start shaking. Again, we can see the nice colors that are forming once they start dissolving. And if we stop these, we'll see that the iodine went into the hexane layer and the cobalt 2 chloride went into the water layer. And let's see how we did here on our questions. All right, looks good. And the I2 went into the hexane because hexane is non-polar, iodine is non-polar. Water is
Polar.
polar, cobalt 2 chloride is, it's not actually polar, this one is actually ionic. But because water is a very highly polar substance, it will also dissolve ionic compounds. So any questions on the demo here for today?